Hey guys, this video is about exponential and logarithmic models. It goes with the other stuff that we've done in chapter 5 about exponentials and logs. You should have seen the first type example we're going to do before, which is about compound interest, and then we're going to talk about half-life, which you may or may not have seen before. Okay, there's actually a worksheet that goes with this section, so you can see it in our Canvas under modules. Okay, it's just titled 5.5 worksheet. So I actually suggest that you get a blank worksheet to work on this with me, but the solutions are also posted there for the examples that we're not going to do in this lecture. Okay, so this is our first example, and like I said, I expect that you've seen some compound interest problems before. Okay, so this just says it took 10 years for $600 to grow to $19,205. What was the interest rate if it was compounded continuously? Okay, so remember the formula for continuously compounded interest is this one. Okay, the worksheet also has the formula for non-continuously compounded interest as compounded yearly, quarterly, monthly, etc. Okay, but this is the continuous compounding formula. Okay, so remember A is the amount. Okay, this is like the new amount. Okay, P is the principal. Okay, which is the starting amount. Okay. E, you know what that is. R is the interest rate. Okay, and this is a percent as a decimal. Okay, and then T is time in years. Okay, so just a little refresher there about what those different things stand for. Okay, so our new amount in this example is going to be the 19,205. So we're going to plug that in for A. Okay, our initial amount was 600, so we'll put that here for P. E is just a numerical value. Our interest rate is actually what we're interested in, so we're just going to leave that as R. And then T is 10 years, so remember T is in years, so we'll just put 10. Okay, so now we're solving this for R. This is an exponential equation because the variable is in the exponent. Okay, so the first thing I'm going to do is isolate the exponential part here by dividing both sides by 600. Okay, so now you can see that this is not really a good candidate for using the what am I trying to say? The method where you set the exponents equal to each other, right? Equating exponents, because you can't write this number as a power of e. Okay, so instead we're going to use logs. So because we have base e, we're going to take the natural log of both sides. Okay, and then we're going to simplify. So on the left side, there's no real need to simplify this because you can input it into your calculator in just this way. Okay, and over here, this is going to simplify to 10r. Okay, now the last thing I need to do to isolate r is to divide by 10. Okay, just like this. Okay, so here's my exact answer. Okay, and then I'm going to plug that into a calculator to get my approximate answer. Okay, now I actually did this before, so let me just look at my answer. I got 0.3466. Okay, now remember that R is the interest rate, which is a percent, but it's written as a decimal. Okay, so you would say the rate was 34.66%. Okay, And you can see that's why I actually rounded to 4 decimals here, is because when you change it to a percent, you end up with 2 decimal places. Okay, you could also round to 3 decimal places here and end up with 1. Okay, but if you round too early, if you round this to 2 decimal places, then your percent is not going to be super accurate. Okay, so we see the interest rate was 34.66%. Okay, all right, let's do one more problem like that. Okay, still compound interest. So this one says it took 10 years for an investment to grow to $2,000 at 2% interest compounded continuously. Okay, what was the initial investment? Okay, so again, we're going to use this, A equals PE to the RT. Okay, so it's growing to $2,000, so this is our new amount. Okay, the question is actually what is the initial investment? So we're going to leave P as our variable. Okay, E is just a numerical value. Our interest rate is 2% or 0.02. Okay, and it takes 10 years, so T is 10. Okay, so the first thing I'm going to do is actually just multiply these. Okay, so 0.02 times 10 is 0.2. Okay, and now this is my variable P, right? So this is actually a numerical value, right? It's just a number. So if I want to isolate P, I'm just going to divide by this numerical value. Okay, so I'm just going to take 2,000 and divide it by e to the 0.2. Okay, and this would be my exact answer. Okay, now I wanted to do this problem because a lot of times people assume that all of these problems you're going to have to use the log because you have an exponent. But this is a numerical value. Like, for example, if you had 2,000 equals p times 2, you would just divide both sides by 2. And that's basically what we're doing here. We're just dividing this number away. Okay, so again, if you want an approximate answer, you need to use your calculator. Okay, so if I do that here, I get 1,637.46. Okay, and 2 decimal places makes the most sense in this example because we're talking about money. Okay, so what would my sentence answer be? The initial investment was about $1,637.46. Okay. Don't forget with these questions, because you have a word question, you need a word answer, right? So all of your answers should have some sort of sentence with them. Okay. All right. One last one about compound interest. How long would it take for an investment to double if invested at 10.5% compounded continuously? Okay, so again, because it says compounded continuously, we know we're using this formula. Okay, if it says compounded annually, compounded biannually, something like that, you need the other formula. Okay, so here, it doesn't say what the initial investment is, and it actually doesn't say what the new value is either. Okay, so our only clue is that we want it to double. Okay, so we know that this number is double the original number. Okay, the original number is P, so our new number is double that, or 2P. Okay, and again, we don't know P, so we can't fill anything in there. Okay, E is a numerical value, so we're not looking for that. 10.5%, okay, is the same as 10.5%, okay, which we can write as 0.105. Okay, and then because it says how long, we're actually looking for our variable t. Okay. All right, now it looks like we have too many variables here because we have p and t, but think about what the first thing you would do is if you're solving this for t. You want to isolate the exponential, so the first thing you're going to do is divide both sides by p. So let's do that. Okay, so I've divided both sides by p. You can see these are going to cancel and these are going to cancel. So it's actually not important what p is. Okay. All right. Now I'm going to try to isolate t, right? I have my exponential equation. I can't use equating exponents, so I'm going to take the natural log of both sides. Okay. This is going to let me simplify. Okay. And then I'm going to divide both sides by 0.105. Okay, so here's my exact answer. All right, and then my approximate answer, I'm going to use my calculator, and I got 6.6. Okay, so how long would it take? Okay, we would say about 6.6 years. Okay, to double. All right, so before we move on to a different type of example, I want to talk about two things. One, you want to be sure that you're giving your exact answer, right? So we're not going to, at this stage, plug in natural log 2 to the calculator and write some decimal here, right? You're going to wait until the very last step to plug into your calculator and plug everything in at once. That lowers the amount of rounding error that you get, and it also shows me that you algebraically understand how to isolate t, okay? Even though this is a symbolic numerical value, okay? And the other thing I wanted to say is about the rounding. Sometimes people are confused, how many decimal places should we use? I think in some examples it's obvious. If it's money, you want 2 decimal places, that kind of thing. And otherwise, 1 or 2 decimal places is usually appropriate, unless it says something specifically in the question. Okay. All right. So we're going to move on to another type of example, and we're going to talk about half-life. Okay. So first, let's say what the half-life is. Okay, so when you have a radioactive material, it's actually emitting radiation, right? That's why it's called radioactive. And as it emits this radiation, the material changes from its radioactive form to a more stable isotope. Okay, so that occurs at a constant rate depending on this material itself. So the different types of materials have different lengths of time that it takes for things to decay. Okay, so the half-life measures the amount of time that you need for half of your original sample to decay to the stable form. Okay, so for example, if you had 10 grams of radioactive material, the half-life would tell you how long you needed to wait until there's only 5 grams of radioactive material. Okay, the other part of the material isn't gone, it's not like it disappears, it's just not radioactive anymore. Okay, so like I said, this is specific from material to material, so normally in the question it will give you the answer to how long is the half-life. Okay, all right, so let's talk about this example. Oh, one more thing I wanted to point out, you can see that we did example 3 here, okay, and now we're going to move on to example 5. Example 4 is in the worksheet and the solution is posted, okay, so I encourage you guys to work on that one on your own and then to check your solutions, okay. All right, so in this one we're talking about radioactive iodine. So the half-life of radioactive iodine is about 60 days. We're going to suppose a nuclear accident gives off an initial amount C of radioactive iodine. Okay, not a great scenario, but there we go. That's a setup for the problem. And we're going to write an equation for the amount of radioactive iodine present T days after the accident, okay? Now, because you have something that's decaying at a steady rate, we know that this is going to be exponential decay, okay? So, just like you guys know that something doubling in a certain amount of time or tripling in a certain amount of time gives you exponential growth, something halving in a certain amount of time is also giving you an exponential function, but it's exponential decay. Okay, so remember, we're talking about the basic setup looking like this. Oops, that's an A. Right, so this is our basic exponential function. Okay, remember A is the initial amount. Okay, and then B is called the growth or decay rate. Or factor, okay? So in this example, because we're having less material over time, this is going to be the decay factor, okay? So what we're going to do first is plug in our initial amount, C. Okay, we don't know what that number is, but we do know that that's the initial amount, okay? Then the only other thing we know is that half of it will be gone after 60 days. Okay, so we know that the new amount will be 1/2 C, right? Just like in the previous one, we had double the initial amount, we put 2P. Here we have half the initial amount, it's 1/2 C. Okay, this is the same. We're trying to figure out B, by the way. Okay, so that's our goal. We want to find B. Okay, because we filled in the initial amount, now we want to know what the growth or decay rate is, right? And we know that this is after 60 days, so we're going to put 60 here. Okay. All right, so I'm going to divide both sides by C. Okay. And then I'm going to get rid of this 60 by taking the 60th root of both sides. Okay, remember when you have a numerical exponent, you can take the root to get rid of that. Okay, now this side I'm going to write in exponential form. Okay, and here I can say the 60th root of b to the 60 is just b. Okay, so now I have my value for b. I can write my function. Okay, all right. So I switched to t because the question says t days after the accident. So I'm going to use t as my input variable. My initial amount is c again, and now I know my b is 1/2 to the 1/60, okay, to the t power. Okay, and I'm actually going to simplify this by multiplying these two exponents together. Okay, so that's my equation for the amount of radioactive iodine T days after the accident. Okay, so that's just part A. All right, so let's look at part B. How long would it take for the iodine to decay to 20% of its initial amount? Okay, so I'm going to start with the equation that we just wrote in part A. Okay, all right, and it's telling us how long, so that means T is going to be our variable. And all we know about the new amount is that it's 20% of the initial amount. Okay, so that's going to be 20% of C, right, which is going to be 0.20. Okay, so that's what I'm going to put here. Okay, I'm going to isolate the exponential part, so I'm going to divide both sides by C. Okay, and now I want to remove I want to get this down out of the exponent. Okay, so there's kind of two different things you can do. You can use log base 1/2, or you can just use log base 10, right? It depends on what you're comfortable with. So I'll show you the log base 10 method in case you haven't seen it. You could also use natural log, by the way. You just want to use one of the log bases that appears on your calculator. Okay, now we're going to use the log rules to bring this out in front. Okay. And now I'm going to divide by log of 1/2. Right, and now I'm going to divide, or I'm going to multiply both sides by 60. Okay, so all right, so there's my exact value, and then if I want an approximate value, I would use my calculator. Okay, so I would get 139.2. Okay, all right, just to be clear, I wanted to show you guys how you could get that using the method that we talked about before. Okay, so where we were at was we had 0.2 equals 1/2, okay, to the t over 60. Okay, so you could also use log base 1/2, so we do that. Okay, so log of 0.5, okay, equals log base 0.5 of 1/2. Okay, now this doesn't simplify. Okay, here, this is going to simplify, and you're going to get t over 60. Okay, now, and we're going to multiply this by 60 to isolate t. Okay, now the issue with this is if you want to get an approximate value, you can't input this. Okay, there's actually another issue with this that I'll mention later. Okay, now how would you do this? You would use the change of base formula. Okay, so that would give you 60 times log base 10 of 0.2 over log base 10 of 0.5, okay, which is actually exactly what we got using the other method. Okay, so either method is presumably fine. Okay, now the real issue with this method is that the base of a log is supposed to be greater than 1. So by using log base 0.5, we're actually breaking that rule, and that's why I didn't initially use this method. Okay, so for another log base like 2, this would work just fine, but because we have something that's less than 1, this is technically incorrect. Okay, so that's why I said the other method might be a little bit better. Now you've seen them both, though. Okay, so let's go back to that question. All right, so we would just say about 139.2 days. Okay. All right, that actually makes sense. If you think about it, you would have 50% after 60 days. So after 120 days, you would have 25%, right? Because the amount halves again. And then after a little bit longer, right, then you would have 20%. All right, so part C of this question says, suppose the initial amount was 15 grams. How much is left after 30 days, 100 days? Okay, so again, we're going to start with our equation. Okay. Now it says the initial amount, C, is 15, so we're going to plug that in. Okay, then it says how much would be left after 30 days. So that means I'm going to plug in 30 for T. Okay, and now because this is all a numerical value, you can plug this straight into your calculator. And the only thing I would do, honestly, is change this to 1/2 instead of 30 over 60. Okay, now if you do enter that, you should get about 10.61. Okay, and if you do the same thing for 100, so you would do 100 over 60. Okay, and again, the only thing I would do to plug this in is actually simplify the exponent, right? You would get 5 over 3. Okay, and for that answer, you would get approximately 4.72. Okay, all right. Okay, so let's move on to our last example about half-life. Okay, now this question is about carbon dating. Carbon dating is a process that they use to age items that are made of organic materials, meaning materials that have carbon in them. Okay, there's actually a super small amount of radioactive carbon in all organic matter. Okay, and they measure that amount and compare it to the amount that should be in a natural piece of that material, and that's how you can age something. Okay, so that's what this is about. Okay, so we can say a piece of ancient charcoal contains 65% as much radioactive carbon as a piece of modern charcoal, right? So that means some of it has decayed away over time. How long ago was the tree burned or turned into charcoal if the half-life of carbon-14 is 5,715 years? Okay, so again, we're going to need to write our own equation. So we're going to start with the base form, a times b to the t. Okay, now we don't know the initial amount again, so we're just going to leave it as a. Okay, now we do know that half of it is gone after 5,715 years. Okay, so again, we're finding b. We don't know a, we think it probably doesn't matter, but we're going to use this information to find b. So I'm going to divide a from both sides. Okay, and then again, I'm going to take the root. All right, so again, I'm going to write this in exponential form. Okay, and over here, this simplifies to b. Okay, so this leaves me with my equation 1/2 t over 5,715. Okay. All right. Right, you can see that we're just plugging this value of b into this equation here, this one. Okay. All right. So then how long is something that has 65%? So we're going to start with our original equation, the one that we had just now. 1/2 to the t over 5,715, like this. Okay, and we're going to plug in 65% of the initial amount, so that would be 0.65a. Okay. All right, so we're going to look to isolate the variable t, right? So the first thing we're going to do is isolate this expression by dividing both sides by a. Okay. Now that we have that isolated, again, because this base is less than 1, we don't really want to use log base 1/2. So we're just going to use log base 10 or natural log. Okay, so this time I'll use natural log just for variety. Okay, so this is just a number. We're going to leave that. Okay, and over here, I'm going to use the exponential rule about logs to bring this out as a coefficient. Okay, now I'm going to divide both sides by natural log of 0.5. Okay, and then multiply both sides by 5,715. Okay, so there's our exact answer. We're going to plug this into our calculator to get an approximate answer. Okay, and I got 3,551.8. Okay, so don't forget to write your sentence answer. This says, how long ago was it turned into charcoal? So we would say about 3,551.8 years ago. Okay. And this is actually a real process that scientists use to measure the age of things that they find in the soil or ancient artifacts or that kind of thing. So it's definitely a more realistic example than maybe you've seen before. Okay. Now, there are other examples on the worksheet. I think there's questions 7, 8, and 9. I encourage you guys to do those ones on your own. They're based on this stuff, and then you can check your answers on the answers that are posted on Canvas. Okay? I hope this makes sense to you guys, and I'll see you guys soon.